Hi all, welcome to the next topic of Unit 3, Sign Magnitude Division. So in today's lecture, we'll see the topic of Introduction to Binary Division, then hardware implementation of a sign magnitude division algorithm, and what do you mean by a divide overflow. Coming to the introduction, we have already discussed binary division as a part of a binary arithmetic. So the division of two fixed point binary numbers in a sign magnitude representation, it is done by the cycle of successive compare, shift and subtract operations. So you are going to, for example, if you consider a 147 divided by 11. So in here in this example, this 147 is considered as your dividend, where 11 is considered as your divisor. So when you perform a division operation on these two values, you get two values. One is a quotient and other is a remainder. So 13 is nothing but your quotient and 4 is your remainder. So in a division operation, you have a dividend, divisor and resultant quotient and remainder. So for example, if you take this division operation, this particular uh, number is said to be called as your dividend. Which whatever number you are dividing this particular dividend with is called as your divisor. So when you divide it, you have to, as a part of it binary division, you need to perform a comparison operation of the bits of the dividend with the divisor. So initially the 4 bits of the dividend has to be compared with the divisor. Only when the dividend bits are greater than the divisor, then you are going to perform a subtraction operation. Here you are going to subtract this dividend from the divisor. Now you get some result. So these results are called as your partial reminders. These are not your actual reminders, the partial reminders. And each and every cycle you are going to shift your dividend 1 bit. Then you are going to perform a shift operation. And again multiply it with the divisor and perform a subtraction operation. So finally you will get a remainder. This is how a division operation will be performed. So if you see this example, this is my division, this is my dividend and this is the divisor, right? So we have to always ensure that the number of bits of the dividend should be, if the number of bits of the divisor is n, then the number of bits of the dividend should be 2n, 2 into n. So here when I am taking this dividend and divisor, my divisor is 5 bits. So my dividend should be 2 into 5, 10 bits. Okay, so 10 bits. Since I have only a 5-bit dividend, I have to add zeros and make it a 10-bit dividend. Okay, so initial I am adding zeros to my dividend. Now you perform a division operation. So initially the first 5 bits of the dividend are checked with the divisor. The dividend has to be greater than the divisor, then only you can perform a division operation. So 01110 is less than the divisor. So here we are considering the dividend as A and the divisor as B. Since it is less, we are going to multiply it 0 times. So 00000. So we perform a subtraction, it becomes 11100. Now I am shifting this 1110 and here this 0, there is no value. So here this 0 will be shifted down. So it becomes 11100. Now 11100 is greater than, the dividend is greater than the divisor 10001. So multiply it 1 time. You get 10001. Perform a subtraction. This becomes 0. So you have 10111. Now again perform a shift operation. Move it here. Now it becomes again multiply it by 1. 10110 is greater than 10001. You can convert these numbers into binary and check whether they are greater than or less than. So I am multiplying it again by 1. So it becomes 10001. Subtract this dividend and the divisor. You get a value of 101. So again shift 10. It becomes 1010. So you cannot perform a division because the dividend is less than the divisor. So I am placing 0 here and I am again shifting one more 0 here. It becomes 10100. So subtract it one time, it becomes 10001. So it becomes 0011. Now you shift this 0 also here. So your remainder will be 110. So your remainder is 110, whereas your quotient will be 01101. Okay, this is how you perform a binary division. Next, so if you look at this, the bits of the dividend are examined from left to right until the set of bits examined represents a number greater than or equal to the divisor. So you have to first check with the bits of your dividend. So the bits of the dividend has to be greater than the divisor. Until then you have to place zeros in your quotient part. Next step, until this event occurs, zeros are placed in the quotient. When the event occurs, so whenever it is satisfied the condition, then 1 is placed into the quotient and you are going to subtract your divisor from the dividend. So whatever you get here, that is said to be called as your partial remainder. So all these are said to be called as your partial reminders. Okay. At each cycle of the process, an additional bit from the dividend is appended to the partial remainder. Additional bit from the dividend, you are going to add to the partial remainder and continue the division process. So until the result is greater than or equal to the divisor. And this process will be continued until all the bits of the dividends are exhausted. Until the dividend bits are completed, you are going to complete the division, perform the division process. So this is the binary division. So next, coming to the hardware implementation of a sign magnitude division. So here it is similar to a multiplication implementation with a small changes. So if you consider, there are three registers A, B and Q. So B register is used to hold your divisor. So the divisor will be stored in a B register and the sign bit of your divisor will be stored in a flip-flop called BS flip-flop. Similarly, we have A and Q registers which also have a sign flip-flops AS and BS. A and Q registers are used to store your dividend. As we know, if the divisor is an n-bit divisor, then you need to have a dividend of 2n bits. So, if you take this example, your divisor is a 5-bit divisor, whereas your dividend is a 10-bit dividend. So, in that case, if you consider a register, it stores only 5 bits. So, for storing your dividend, you require 10 bits. So, you require two registers. So, the dividend will be stored in two registers A and Q, whereas your divisor will be stored in a single register B. Okay, and the signs of the dividend is stored in both the flip-flops AS and QS. Okay, now after performing the division operation, the contents of A and Q will contain Q contains the quotient and A contains the remainder after the entire division operation is performed. But at the starting, AQ contains the dividend. Part of the dividend will be stored in the first half of the dividend will be stored in A register, whereas the second half of your dividend will be stored in a Q register. And the sign will be stored in AS and QS. So here also, as a part of your division operation, you have to perform a shift left operation on the contents of E, A and Q registers. The CAQ is shifted to the left with 0 inserted in the qnth and the previous value of E is lost. So in this case, the 0 will be inserted to this end and whatever is the value of E, it will be lost. So the MSB bit of A will be moved towards E, whereas the MSB bit of Q will be moved as an LSB bit of A, and qnth bit you are going to insert as 0. So after performing a shift left operation, you are going to perform a subtraction operation. The dividend is shifted to the left and the divisor will be subtracted by adding it to complement value. So after performing a shift left to the dividend, you are going to subtract the divisor from the dividend. How do you subtract? By performing a 2's complement of the divisor and adding it with the dividend. And after performing this particular addition, whatever is your end carry, which is stored in a E flip-flop, that will give the additional information about the magnitude part of your result. So this is all. We'll see it in much detail in the flow chart. So when it comes to hardware, so you have a B register which holds your divisor, A and Q which stores your dividend, and sign bits holds the signs of the dividends and divisors. E flip flop, whenever you perform an addition operation on the contents of your divisor and the dividend, the parallel adder performs an addition and the result carry bit will be stored in E flip flop and the result will be stored in A register. And after the entire here also we have a sequence counter. So the sequence counter is initialized to a value equal to the number of bits of your divisor. Okay. So after the division operation is performed, finally the quotient will be stored in Q register and the remainder will be stored in a register. And Q and bit represents the rightmost bit of the content of a register Q. So this is the hardware implementation. In case of a division operation, there is something that we get which we call as a divide overflow. In case of a addition operation, you get an add overflow, right? AVS flip-flop. So whenever you have an overflow out of your addition operation, you set the AVS flip-flop to 1. Similarly, in case of a division operation also, if the quotient, in case of a quotient, it results in an overflow. That is said to be called as your divide overflow. So we know that the quotient is stored in a register Q after a division operation has been completed. So there is a possibility that the quotient requires, say for example, when you are performing this division operation. So in this example, if you consider your quotient is only a 5-bit quotient and the register the size of your quotient register, it holds only 5 bits. So there is not a problem. This is not a problem. But if you consider this particular example, the quotient is a 8-bit quotient. So you're getting a quotient here which is 8 bits. But when you do this division operation on a pen and a paper, there is no problem no matter how many number of bits you get for your quotient. But when it comes to a hardware implementation of a sign magnitude division algorithm, your quotient register can hold only 5 bits of data. If there is any overflow, if the size of your quotient requires more number of bits, then you call it as a divide overflow. So in this example, the quotient requires more than 5 bits. So your register Q is not enough or not sufficient to store your quotient because of its limited size. So this situation is said to be called as a divide overflow situation. So the quotient is to be stored in a standard register. So the overflow bit will require one more flip-flop for storing the 6th bit, or it may require one more register to store the additional bits. So the divide overflow condition, this type of condition is said to be called as a divide overflow, and this condition must be avoided in a normal computer operation. So in order to avoid that, what do we have to do is we have to make a provision in order to ensure that the particular condition has to be detected and it must be included, the detection hardware, it must be included in the hardware or the software so that the detection will be done beforehand itself. So when the dividend is twice as long as the divisor, the condition for the overflow can be stated as, when how do you detect it is, a divide overflow condition occurs if the high order half bits of the dividend, we are storing our dividend in two registers A and Q, right? So whatever are the first 5 bits, 5 MSB bits of your dividend which are stored in the A register, if it is greater than or equal to the divisor, then we say that overflow has occurred, which means that the quotient cannot accommodate in a 5-bit register. So in that case, we call it as an overflow. So in this type of situations, overflow has to be overflow. There is a flip-flop, special flip-flop present in your hardware. We call it as a divide overflow flip-flop DVS. So whenever this condition is satisfied, the hardware will come to know that there is a divide overflow situation in this in that particular problem, and it will set the DVS flip-flop to 1. So another problem associated with the division is that the division by 0 must also be avoided. So your hardware of a software should have a provision to identify these type of situations which occurs in a division operation and take the proper measures such that it doesn't cause any wrong results. Okay. See the remaining in the next class. Thank you.